Hi everyone, I'm Christophe Pinte and I'm going to present some early results from the exoALMA large programs. This is a big collaboration and I've highlighted all the people at Monash who work on that. It's mostly PhD students and I try to show you their work. So you've shown talks by Kathleen and Tom before. So what's the motivation for exoALMA? So 10 years ago, ALMA came online and when the long baseline became available, we got this famous image of a shelter. And the main question that arose was like, was this gaps and rigs everywhere in this disk? What is causing it? Are they caused by planet? And this question is becoming more and more important because every time we look at the disk with ALMA now, we see structure everywhere. So they all have, most of the structure are rings and gaps, but we see like big cavities like that one. We see asymmetry. So there's a lot of structure. And basically every single disk we look at is full of structure. So this is suggested that there's some planet interaction happening in those disks, but there could be many other mechanisms explaining those structures. So to be able to distinguish, we want to be able to find the protoplanets. How do we find protoplanets? Well, it's very difficult. So the classical method, transit and radial velocity, you cannot really use it because you need your system to be close to Edgen. And if your system is close to Edgen, you have the disk in your line of sight. The disk is optically thick. You can't see the star. So you cannot do transit or radial velocity. What could we use instead? Well, we could use direct imaging, but direct imaging is very tricky because most star-forming regions are quite far, typically 150 parsec, which is much further away than the planets that are usually detected by direct imaging. In some cases, you can be very lucky. So in that, this is a famous detection of PDS 70, which is a disk where there's a big cavity that has been cut, and you have two protoplanets that have been detected. But in most of the disk, you get something like that. You get a beautiful image of the disk, but because the disk is optically thick, you can't see any planet that might be embedded in it. And in that one, for example, you see a hint of spiral, so it's probably a planet, but we cannot see it. And in practice, direct imaging has been very difficult. People have tried many times, and there's many detections that have been claimed. But you can see that it looks very messy. You have structures, and it's very difficult to distinguish between a real detection and artifact of the data processing. One that's very exciting, that's a detection there that has been recently confirmed by Ian here at Monash, where we can see the Kepler motion in the planet. But again, for that one, I think it's kind of lucky in the sense that there's a big gap that is quite deep, which allows us to see basically through and detect the planet. But in most cases, it has been very difficult, and there's only a handful of detections that have been done by direct imaging. So what can we do instead? Well, if you have a planet in a disk, simulation by the phantom code, you generate a nice spiral, and the spiral, you have a spiral in density, but you also have a spiral in velocity. So because the planet is perturbating the velocity field, you might be able to detect that. And what does it look like? So this is another set of simulation, but if you put the same thing, a planet in the disk, you get this spiral that generates kinks near the location of the planet. So the idea is that we can try to detect those kinks to find embedded planets in the disk. And that's exactly what we detected in 2018. This is a disk around a big star. So you have the star in the middle, you have one channel map, and you see that at this location, you have a kink, which suggests that there's an embedded planet. The amplitude of the deviation is about 15% of the Kepler velocity, and you can use that to try to measure the mass of the planet. And the interesting thing is that in that side, you have a kink, but if you look on the other side, the symmetric side of the disk, there's no kink at all. So this deviation is really localized in the disk, which implies that it's something really inside the disk that's causing this deviation. So very likely a planet. So what have we been doing with that? So you have at the top the different observation of the same disk with ALMA in different channels, and you see the kink in the middle. And we have run models combining the hydro code phantom with the radiative transfer code MC First. And we try to compare our simulation with different planet masses with the data, and you see that for one Jupiter mass, the kink is a little bit too small. For 5 Jupiter masses, the disk is a bit too big, and so the planet is probably between 2 and 3 Jupiter masses. So we can use this kind of ALMA observation to try to weigh the planet in the disk. So this is all good, but we want to do that for many objects. So how do we do that? Well, we have a large program that's called exoALMA. So exoALMA is observing, has observed 15 sources. So it's a very biased sample because these observations are very difficult. So we targeted the brightest and the biggest disk. We targeted 3 lines, and we have more than 180 hours combining the 12 and 7 meter arrays of ALMA. And we reach a new level of data quality with 28 meter per second spectral resolution and 0.1 arc second. And what does it look like? This is the 15 sources of exoALMA observing 12 CO in peak intensity, and we get these beautiful images. And the most obvious result of exoALMA is that all those disks have some structure in them. You can see a spiral here, this disk and a spiral too. So most of them seem to highlight spiral. And what does it look like if you look in more detail? If you look at the channel map, this is the kind of data quality that we have now on the disk, where we have like amazing cubes where we can really see and map in detail the surface of the disk. So this is one disk that's incredibly smooth. They're not all like that. Some of them are very disturbed, like this one. So we have a huge variety of kinematic structures in those disks. So to try to understand them, we came up with a very simple procedure that's summarized here, with no many steps at all. But the idea, and so this talked before by Tom and Kathleen, we tried they use slightly different method to try to extract information from those cubes. But the main idea is we try to make sense of those cubes. So we try to subtract a model of the Keplerian rotation to highlight the potential deviation from the Keplerian rotation. And what does it look like in practice? So here you have an example of 4 disks. You have at the top the continuum. So the continuum, as I was showing before, we know there are structures like gaps and symmetries, and this is the corresponding structure that we see in the CO emission. So be careful that the scale between the two is not the same. The CO emission is much bigger than the dust continuum, but you see we can extract those spiral much more clearly. But we were already seeing them in peak intensity. So to the spiral that we see in intensity, there are also spirals that are corresponding in velocity. We will, of course, try to go further than that. So we've done, the plan is to do detailed modeling of all the sources in the long term. And one step toward that is we have compared all the hydrocodes, including Phantom here at Monash, and they all give us very good agreement. So we're very confident in the numeral codes that we have been using. And one exciting result of the exoALMA large program is that it looks like that in at least 5 of the disks, there's some indication of planets. So you have those 5 disks here, and you see that as before, for the first days of the ocean, there's some kinks in all those individual channels that look like they might be caused by planets. So in this sample of 15 disks, there's at least 5 where we believe there might be planets. Which is a very exciting result. So as a summary, the main result of exoALMA, I think, is the disk. All of them are extremely dynamic. There's a variety of structure in the gas and in the kinematic of the gas, as they are for the dust. It's not clear yet if they correspond one-to-one, and we need to understand a bit better for that. The quality of the data allows us to map the 3D physical and dynamical structure of the disk. We've detected some planets in the sample, and there seems to be a relatively large number of them. And we have James Webb and ESO follow-ups with the ERIS instrument in the near-infrared. So that James Webb is mid-infrared and ERIS is near-infrared, to try to get a direct image of the planet. And the idea is basically to try to start constraining the formation process of those planets, because the kinematic will give us a mass, and with photometry we'll be able to get the luminosity. So we'll be able to tell how bright the planet of a given mass at very early stages. All those disks have a few million years old. So we basically, hopefully, do the first step toward being able to constrain the formation mechanism of those planets. Thank you.
Really impressive and beautiful work. I'm curious about this result. If I understood correctly, maybe a misunderstanding, that you only see the kink on one face of the orbit, not on the other.
Yeah.
And that means, if I understand correctly, does that imply that maybe the planet and the disk are not the same plane? the orbital?
No. So the planet, we believe, is in the midplane, and the planet is generating a wake, and the velocity deviation are stronger near the planet. So basically, what we see is the beginning of the wake. So we see this blue-red flip in velocity that distort the isovelocity contour, which correspond to this kink in the map. And in practice, we detect what we call secondary kink because we know that we have better data quality. We can map the full wake. So this is the main thing that you see there, but basically it's a wake and it's coming around, and you see here there's another kink, and that's basically the wake that's wrapping around. And so this is the early dataset. With a better dataset, we can actually map the full wake of the planet, which is similar basically to what we see in this kind of structure, even if I believe that one is more like a binary star on the planet. But with the data quality that we have now, we're able to map the full interaction of the planet or binaries with the disk.
Thanks for the breakdown. So when you're doing this sort of velocity residuals, do you need to use other information from other observations, or does it just, on the sort of like fitting with ALMA?
It's more so we use the distance, but apart from that, we're extracting everything from ALMA because we have basically velocity curves, so we can extract the central mass, and we can also extract deviation in the Keplerian profile, for example, the pressure gradients and things like that. And the idea is to try to remove all those things to only leave what would be due by perturbation by a body to try to constrain the planet mass.
No, sorry if I missed this. I was just wondering on the possibility of multiple things from multiple planets and how the velocity is not overlay.
Yeah, so that's, I mean, they're messy, so it's very likely that there's multiple kinks that might be created by multiple planets. We haven't looked in detail into that because, of course, it's already complicated enough to fit one planet, but it's probably likely.